Hi, everyone. Thanks for joining. Appreciate it, especially the last session of the day here. Today, Kaushal and I are going to be talking about exploratory analytics at enterprise scale. So I'm Sean Kandel, founder and CTO of Trifacta, and Kaushal is a senior engineer at Trifacta. Just right out of the gates, we are a data preparation company. A lot of what we're going to talk about today is data preparation and about data preparation. But as much as possible, we're going to try to talk about kind of general best practices and trends we've seen, not really focus on specifics of any one product, including ours. We'll show some small, quick snippets of products, one of which is ours and another product in the space. But really, if you want to find out more about what we do or other companies, I encourage you to ask questions afterwards or visit the booth. So diving into the topic, first I just wanted to say, what do we mean when we say kind of exploratory analytics or data exploration? I think the easiest way is to really contrast it with more static workflows. So I'd say, a lot of workflows today, you have kind of known inputs and known outputs. You can build kind of a highly optimized data pipeline that translates those inputs to outputs. And there is some monitoring, some kind of tweaking of those workflows over time. But generally speaking, there's not a ton of iteration in those workflows. What we're kind of more interested in today is talking about kind of more exploratory workflows. This could be new analytic projects. It could be doing feature engineering for machine learning algorithms. It could be building kind of a new dashboard. But the idea is that you have kind of maybe known inputs or maybe unknown inputs, and you're iterating to get to, again, either a known output or a potentially unknown output. And you get in this kind of highly iterative process where you might discover new things as you go, things you weren't expecting in the data, or you might decide your original hypothesis was incorrect and you want to test something new. And what we're going to talk about today really is, given that you're in this iterative workflow, how do we make this more efficient? And there's really kind of three broad ways we'll talk about. One is to make the loop smaller and tighter, so you're iterating faster. The second one, especially when we start talking about kind of at enterprise scale, is having more people contribute to the analytic process, especially people who have kind of the best domain expertise, so that you kind of, in effect, get multiple iterations going at once. And then I think kind of an overlooked, but probably in some ways the most important inefficiency we'll try to address is, when you have multiple people who are all working in parallel, how do you kind of effectively share each other's work, leverage each other's work, so you're not having wasted effort across the organization? Talked a little bit about exploratory. Kind of the second piece we want to talk about is kind of what we mean when we say enterprise scale. I think a lot of people talk about large data volumes, and certainly we want any solution to kind of work with large data volumes. But I think kind of the other three things we see at kind of large organizations with a lot of analytic use cases is that you kind of have this growing number of users and consumers of data. So we want to talk about both how do we kind of empower them to work with data, but also Kaushal will talk a lot about how do you actually architect a system so that when you have hundreds or even thousands of users kind of exploring over the same data and using the same resources, how do you kind of scale that out? Similarly, as you get more users, you get more diverse use cases, so optimizations can become harder. And then the last thing we'll touch on only briefly is how you have a system that kind of can last over time. As kind of technology evolves, execution environments evolve, how do you make sure your work can still be leveraged over time? So I think the first thing to note when we kind of looked at kind of broad trends in the industry, the two kind of main areas that have gotten a ton of investment over the last couple decades, and really over the last decade in particular, are kind of data platforms and data analysis tools. So if we look at the platform side, you have Hadoop technology, so Cloudera, Hortonworks, MapR. You have cloud technologies as well that have made it kind of more cost-effective to store more data than ever was possible, process data faster and cheaper than ever before. So kind of tremendous innovation in the last decade or so. Kind of at the same time, there's been a ton of innovation in reporting tools, visualization tools, machine learning products, in some sense, have also become kind of widely accessible and much cheaper. And what we found is kind of the piece in the middle is still kind of underserved. So what do we mean by this piece in the middle? It's really kind of taking data in its raw forms from the diversity of sources people want to analyze data from and kind of make sure it's high quality and in the right format so that you can easily consume it in your downstream analytic tools. So as mentioned before, again, kind of full disclosure, we are a data preparation company, but we're going to try to talk about this a little more broadly and some best practices here. But what we've seen is that there's kind of this new bottleneck, partly because the other parts of the tool chain have just gotten so much better, but also partly because this part was kind of widely ignored for a long time. So just some examples of what we mean when we talk about data preparation. It's kind of a very wide spectrum of things, but it could be working with data that's kind of unstructured in, say, a spreadsheet, so things like missing records, or data that's kind of organized in disjoint matrices. It could be working with kind of semi-structured data and mapping it to structured data, maybe looking at things like log records and parsing out relevant fields. You might have kind of heterogeneity across records. You might have structured data, but that's formatted in different ways. You might want to kind of pivot your data or kind of reshape it so that it's in a different structure. Mapping data across tables. So you might have kind of simple cases like this where you're looking from a code to, say, a state name, or kind of more complicated integration problems where you have kind of different levels of granularity. You might have missing data, outliers, duplicate values, or maybe potential duplicates and you're not really sure. So I guess all this is to say is that there's kind of a number of things that can go wrong with data and a number of processes that take place before you can often analyze it, and certainly before you can be confident in your analysis. So this is just a quote from DJ Patel, former chief data scientist for the United States, says that 80% of the work in any data project is in cleaning the data. So again, what we've been interested in this space is really looking at what are some opportunities for improving the tool chain so that that 80% gets shrunk and you can, again, get faster iteration in your analysis process. So I'll kind of talk about three different topics. First, I'll talk about some of like the good opportunities when you use these techniques. But then Kaushal will talk about, well, how do you actually make these things possible and how do you scale this up when you have a large number of users over large data volumes. So the first thing I'll talk about is interactivity. And again, I'll kind of start off by contrasting it with how most existing tools work. So if you think about how data preparation typically works today, you might start off by typically writing a script or maybe using a mapping tool, but you'll define kind of a long series of logic to manipulate your data. You then kind of hit run. And if you're like me, you could sit back, relax for a while, maybe grab a coffee as this kind of batch process runs. Eventually, you'll get some end results back. You'll then kind of need to validate that data. So you've kind of gone from input all the way to output. And then you kind of look to see, hey, is anything wrong in this process? And then if something's wrong, you'll kind of go back through all your logic and try to figure out where did you go wrong in that process. So this is kind of the first, what I would say is kind of loop of inefficiency. We call this the batch loop. You kind of start by writing out your entire logic or your entire script. You then do a long-running job over all your data, and as your data gets larger, it just takes longer and longer to get results. You finally get your results over all of your data, then you kind of sift through that, and you're kind of responsible for finding and fixing any errors, and you get in this long kind of iterative loop. And this is kind of a chart I've stolen from like agile development processes, but I think it applies to most processes in general. The longer you kind of wait to see if you're on the right track or if there's some issue, the higher cost of change that you'll have. So what we're trying to do is kind of move you down this curve. And one of the reasons I think this happens is that the tools as constructed today don't really encourage interactivity. For one, I think the most glaring thing when you look at tools for data transformation is that there's literally no data on the screen. You're working at kind of a very logical level, which encourages you to kind of define out all your logic and then get into this batch loop of execution and assessment. So kind of contrast today with new tools coming out where as you interact with the data and as you build up your logic, trying to give you kind of immediate feedback on a step-by-step basis. So if you're trying to, say, parse out a field here, you kind of see immediately both kind of a sample of what will happen over the raw values, and additionally maybe some summary statistics at the top, like distributions or anomaly reports that try to point out potential errors in your logic or to kind of see if you're on the right track. So the idea here is that if you can give real-time feedback over the data, both in terms of kind of sample values, but also kind of summaries over the data, you'll hopefully get faster iteration in the process. So the idea is to go from this kind of batch loop to a much shorter loop where instead of kind of working over a full script, step by step. You kind of will run your logic interactively, hopefully get some nice validation immediately, and then you can fix those errors immediately on the spot as you're going. And the idea here is that we can kind of move you down this curve from a batch process to an interactive process, and you get that smaller cost of change in the loop. So that first one was really about kind of contracting the loop and making the loop itself more efficient. Now I'm talking about how you kind of encourage more people to participate in the process. So I think one of the ways to do that is by using some predictive technologies. And I think the idea here is that if you look at across the organization, there's often a ton of people who want access to data. But generally speaking, there's only a small subset who actually have the skills necessary to prepare it, to clean it, to assess its quality. And you end up in what we call kind of the dependency loop, where if you're an analyst or someone who wants data, you can kind of ask a coworker for the data. And they'll kind of return results at their leisure. In the best case, maybe minutes or hours, but typically this could be days, weeks, or potentially never, depending on priorities. So again, when we look at why is there this dependency loop, I think it goes back again to the tooling, where a lot of the tooling requires kind of a level of technical expertise to work with data. So I want to show you, this is actually a research prototype from, I think, 2007 that came out of MIT by actually one of the creators of OpenRefine, who you might be familiar with, which is a data preparation product. But this is an example of how you can use prediction to enable people to do kind of large-scale transformation without needing any technical skills. So this is something called simultaneous editing. And the idea is you can kind of automatically cluster data into, in this case, phone numbers, into phone numbers with similar structure using some algorithms, or in other cases, machine learning techniques. And once you've kind of done this clustering, you can allow kind of anyone who knows what they want to do with that data to kind of reformat it in bulk. So again, this is just pointing out you can kind of lower the necessary skill set in order to do these large-scale transformations. There are other tools that allow you to kind of directly manipulate data, like Excel and others, but often that's kind of a more manual, tedious process. So again, just pointing out an opportunity here to use prediction to make the process of transformation more accessible. So again, the idea is here that by using prediction, you can reduce cycle time, but also enable a much wider set of users. So again, going from kind of the longer loop to a shorter loop, we now have an analyst, but instead of asking someone else to help them get their data, they can kind of ask for data through to some type of software or learning algorithm. The algorithm might return some results. It might be wrong, and they can iterate, but now those iterations happen on the order of milliseconds or seconds instead of hours, days, and weeks. So the third one I want to talk about quickly is interoperable. And there's a few different angles on interoperable. I'm going to touch on two quickly. But the first one is really about, now that we have hopefully more users participating in the process, doing work faster than before, hopefully they're not doing a lot of redundant work, and hopefully they can leverage what each other have done. So again, we have a bunch of users now, hopefully working with data. But what we've seen at a lot of organizations is that either individuals or potentially small teams are often kind of work in silos. A lot of shared work and shared knowledge that could be shared potentially actually doesn't get shared. And I think one of the reasons that happens is that when people are working with data, often it's kind of onerous to have to think about, well, should I share this with someone? Who should I share it with? When you're just trying to get your job done. So you end up in what we call kind of a disconnected loop. So as you're working with your data, it's kind of your responsibility to manually capture your metadata and share it out. And then kind of the flip side is also true. If you're in an organization, you might not know that there's something out there that's useful for you. You might not know that other people are working on similar problems, that have done similar transformations. So it's your responsible to kind of manually leverage that metadata. So you end up, again, what we call kind of disconnected loops, where the idea is now you have more and more people working with data, but they're not really leveraging or sharing the work. And there's a bunch of problems that occur there in terms of inefficiencies, and also potentially some errors and other issues, such as repeated work. So you're doing stuff that's already been done before. You might duplicate a bunch of data, again, putting more kind of strain on your resources, and then also potentially producing inconsistent definitions. So you get 2 metrics out of 2 different reports. With, they look like they're the same metric, but you don't understand why they're different. So quick example of that, say we have 2 kind of scripts or transformations side by side here. You might start off 2 individuals. They might kind of parse their CSV files in the same way, so kind of just duplicating their work. They might kind of split an email into username and domain. The other person calls it user, so you start getting these little inconsistencies. Maybe you both filter the data. In our case, we might filter out Trifacta users when we're doing analysis over our logs. Someone else at Trifacta maybe filtered out Trifacta and people using test.com as a domain. When you create metrics, you might get little differences here. For instance, sign-in time versus registration time, and so on. So you can see as if you're not kind of effectively communicating what's been done before, you start accumulating these inconsistencies, this debt, and kind of wasted effort as well. So I think most products try to handle this through kind of explicit metadata sharing, and I think certainly this is, you kind of need this in a product. That I should be able to share my work with others in the organization, and that's certainly important, but it's still, in some sense, the onus is very kind of manual. It's on the user to decide who to share with, and it's kind of up to you to realize if something that's been shared with you is potentially useful. So sorry, I think this is part of the technical difficulty here. So we're not a metadata or a cataloging company, but I wanted to point out that there's a ton of work in this space over the last few years of companies that are collecting metadata that comes out of products like ours and other kind of products for working with data, can help kind of organize that information, summarize it, provide recommendations that help you kind of effectively leverage work. And kind of on the preparation side, I think looking forward over the next few years, I think there's a real opportunity to leverage that metadata to provide better suggestions in terms of what data sets others are using in the organization, what transformations have been applied to them, and so on. So I think over the next few years, we'll start seeing this kind of integration between preparation and cataloging, where we go from this loop that's kind of disconnected to what I call kind of the networked loop. And the idea here is that as you're preparing data, if data preparation products can kind of export that metadata into cataloging systems, those systems can then help kind of automatically kind of organize that data, and then if preparation tools are kind of well integrated there, you can leverage that metadata, and again, you get kind of more knowledge sharing across the organization. And again, the idea there is to move from kind of these siloed, disconnected workers to something that's a bit more networked. The second kind of thing I just want to touch on briefly, and then Kaushal will talk a little bit more about this when we talk about interoperability, is really as you're preparing data, you're building up a lot of work, a lot of transformations. And one thing you've probably noticed is that as technology changes, execution environments change. There's kind of a new engine every few years. That's the most popular one. So I think one of the things that's really important when working with data is making sure that all your work, to the extent possible, is kind of compatible across these execution environments. And Kaushal will talk a little bit more about how to actually do that. So with that, I'm going to hand over. Kaushal's going to get into kind of more technical details around the architecture and how you actually enable some of this technology.
So as Sean mentioned, there are opportunities for interactive, predictive, and interoperable. And so what does interactive and predictive actually mean for the underlying data application? Now, when you first load up the data, you just don't want to load up the raw data, right? There's a lot more information that you need to provide the user so that it is interactive. So on each data load, you have to infer the structure of the data. You have to interpret the types in the data. You want to provide valuable visualizations to kind of summarize the data that a user is seeing, and that could be in terms of profiles. You have more detailed information about the distribution of each column of data. And you also want to inform the user with what's or unclean about the data. So you want to analyze what are the outliers, what are the missing values, what are the incorrect types. So you want to give information not only about the summary of the data, but also the quality of the data. And this has to happen on every user action. As a user takes action, you want to update this information, this metadata, and present it to the user. And that's what makes it interactive, and the user has immediate knowledge. And when we come to predictive interaction, what does that mean for, again, the data application? It means that it has to anticipate user action. It has to anticipate, OK, if a user highlights, let's say, the zip code in an address field, what is the user trying to do? So the underlying model has to understand that, OK, they're either trying to separate it out, identify data rows with this particular field, and it has to provide suggestions back to the user so that the user can quickly select what they intended to do. In addition to that, they might have not thought of options that the predictive interaction can provide, and that essentially improves the usability of the product. So what are the technical challenges with this? In order for a tool to be interactive, you need immediacy. And now, what do I mean by immediacy? There's been research done where essentially user attention is in the order of tens of seconds. And you want the user to stay in the flow and not be distracted to avoid errors. And so the user flow, the interactivity has to be within sub-second. So you have typically less than a second to compute all the information I just talked about and present it back to the user. This includes the summarized data, metadata, as well as the predictive interaction. In addition to that, there's a problem of scaling the unknown. Now, in the past, there are these methodologies for pre-computing, indexing, analyzing schema, and these work very well with structured data and also with very common analytic queries, right? In the case of unstructured or semi-structured data, these might help, but they don't solve the whole problem because the queries that you're trying to run here are a little more complex. There's a lot of string manipulation. There's a lot of changing the shape of the data, like pivoting, unpivoting. And so although these methodologies exist, they don't really solve the problem. So essentially, we want to try and understand what do data exploration applications need from an immediacy perspective, but in the context of enterprise scale. So that means, how does immediacy work with increasing number of users, large data volumes, and collaboration and governance? So I'm going to look at a few data exploration architectures. We'll start off with a single node, which is a desktop application or a single server node, and then we'll see how distributed architectures perform in terms of immediacy. So let's say you have a single node, desktop application, a single user operating on relatively small data. Now, this application scales fairly well with increasing users. You have an installation per user. But as the data volumes increase, due to the limited resources of your desktop, the application either slows down or crashes and directly affects immediacy. So right away, it's not going to scale with the data volumes that you have. Next, let's look at a single node, a server. So the limitation in the previous case was with the compute resources. So you effectively invest in more compute and memory resource. And now you're able to, you're basically able to service more number of users who can interact with larger data volumes. But what happens as the number of users increases? You essentially have contention for the resources on the server node. It's because you have more number of users. You may have scheduled workloads. And as there's contention between the interactive workloads and the scheduled workloads, you run into concurrency issues. And so the only way you can solve this is essentially by throwing more money at the problem. You either invest in a larger server node, which has more compute and memory resource, or you split it up and get more. And as you try to scale this at enterprise scale with more and more users, you're essentially making it cost prohibitive, because the only way to scale is add more buy more of these. So this doesn't scale as far as immediacy is concerned either. So let's go on to a distributed architecture. So now you have a distributed compute storage infrastructure, and you have a large number of users. So there's one class of applications, which is basically they require their own proprietary execution environment, which is separate from your existing infrastructure. So first off, it's an additional cost, which can sometimes go up to twice your actual existing infrastructure. But you're able to ingest large volumes of data and also service users. So the solution does scale with large data volumes, but what about the number of users? So remember we talked about immediacy. And one of the requirements for immediacy is essentially that you need a low latency turnaround for immediacy between the user and the application. So as you're ingesting full data sets, your users are interacting, and the use case is essentially exploratory. So there's a lot of iterations that go on between a user and the application. So let's say they're first reshaping their data, then they're adding more transformations. So what does that mean? So essentially, your application needs to cache multiple copies of that data. And the reason is you want this low latency. So as a user makes one transformation, you make a copy of that data, store it on your cache. And now you're slowly going to run out of memory. So this applies a lot of memory pressure. Now there are multiple ways of solving this, right? So you can either limit the number of cache copies in the cache that you keep, in which case, if a user were to roll back 5 steps back or were to redo something, you end up recomputing, which is a waste of compute resources. Or you end up writing back to your storage. And this introduces an inefficiency loop where you're ingesting data, you're writing it back, and you're starting to saturate the network bandwidth. And as you add more users and you have more scheduled workloads, and you're collecting metadata and processing it, all these are contending for these compute and memory resources, and it eventually lead to concurrency issues and memory pressure. So if you look at this solution, in summary, you're maintaining a lot of copies of the data, you're saturating the network bandwidth, and you're running into concurrency issues and memory pressure. So although the solution scales for data volumes, it doesn't really scale with the number of users if you take immediacy into context. So what can you do about this? So instead of having a separate execution environment, you essentially push the execution into the existing infrastructure. So this does address it helps with scaling volumes, but does it really solve the issue with the immediacy? Well, so you've removed the inefficiency loop between the separate execution environment and the existing infrastructure, and you've reduced the network latency. But as you have more users, you're still going to run into concurrency issues. You're going to still have a lot of memory pressure, although this is less than, you've not completely solved the problem. So for immediacy, essentially what we need is we need to push only the necessary computation closer to the user. And what I mean by this is a user doesn't have to constantly interact with the application on the server. If you push enough computation onto the client, the user can iterate over in the client itself without contacting the server on samples of the data set, not the complete data set. And so the onus is on the application and the server to generate intelligent user-driven samples. The client then is able to close this loop between the user. So a user now has immediacy, assuming the client engine is powerful enough. It can also offload the server from collecting the relevant metadata. And once a user is satisfied with that flow, he or she can verify that intent at scale. And now the user is free to move on to other tasks and is not tied down by waiting for a batch process to complete. And so in summary, if you push all the necessary computation to the client, you only have to maintain one copy of the data because now you're sampling and you're only working on limited samples. You don't have the network latency because you're not ingesting and writing back. And the concurrency issues are fewer because now each individual user is using their own client compute engine to process and iterate over their data. So now let's look at what the computation needs are on the client. So when I say you push computation onto the client, we're not using a scale engine. And the reason for that is scale engines are not optimized for single nodes. They're not optimized for latency. They're optimized for throughput. So one of the needs for the client is speed, which is basically instantaneous feedback to the user. We also want a low memory footprint. And one of the reasons for that is we want to operate on a large representative sample of the data set. And that doesn't happen unless your client engine has a low memory footprint and is using memory efficiently. And finally, portability. The client engine needs to work on a variety of platforms, so you need that portability. So we've worked on designing a client engine, and what we've learned is for speed, you need something that's low latency and multi-threaded. So we've come up with essentially a compiled C++ LLVM query engine that has very low latency and also has a high throughput. Now, the high throughput is essentially to stream data to the user. Now, a user is not visually interacting with the whole sample, but a part of the sample. And if you can stream that data, that tightens the loop even further for interacting. You also want a low memory footprint. As I mentioned, in one of the server distributed architecture designs, we were caching copies of the data sets. Here, you want to cache only samples of the data set to quickly roll back. But you can do it in a smart way by only caching incremental changes. And also having a low memory footprint and good memory management just increases the percentage of the data set size that a user can work on. And as far as portability is concerned, Pinnacle, there's support for Pinnacle on Chrome, and there's a new standard for all browsers coming up later this year on WebAssembly. And you can port that to WebAssembly and be able to use it in the browser. So the plot on the right is essentially where we compare a client engine to a scale engine. And it's a random sample of a 100 gigabyte data set. And over here, essentially, as you increase the number of columns where you're unnesting data or pivoting data, as the number of columns increase, the client engine is still able to respond to the user in a second. But scale engines, because of their large memory footprint, are unable to do so. And finally, about collaboration. So let's say you have multiple users, as Sean alluded to. How do we separate or share data or user flows across members of an organization if they're working on similar data sets but for different purposes? So one of the things you want to do is separate user intent from the implementation. And what I mean by this is, say you have a DSL, and this is a very high-level elaboration of the intent, which is separate from the actual runtime implementation. So if you have that separated, it's easy to extract out logic from your DSL and share it across users, as opposed to the actual script that's generated and then extracting parts of that script. So this makes transferring logic from user to user much easier. It's also easier to share flows, and as a result of that, you're reducing redundant work, improving productivity, and you can apply similar logic across organizations on varied data sets. Another advantage of separating user intent from the actual implementation is longevity. And the reason is because you don't get tied down to an implementation, and your architecture itself is not tied to any one particular runtime environment. As you can see, over time, the most popular platform keeps changing but as that changes, you don't want to keep refactoring or rebuilding your architecture or your data application as that landscape changes. And it also gives you the ability to work with different applications. If I can compile down my DSL, the intent, into an intermediate form, I can then compile down to any runtime that I want. And this makes it more portable across different platforms. Like you could run something on a Hadoop cluster, you could run something on a node, or compile down to Dataflow to run on a Google platform. And so in summary, essentially, what we need for immediacy is essentially a client-server architecture where you offload a lot of the interactivity or enough computation for interactivity to the client, and you get efficiency and you design for longevity. And that's all I had. Thank you for your attention, and we'll be happy to take questions.